I did it. I did it. I made it happen. All right. Close the door now. So, it's Friday. No song of the day today. We'll probably listen to some music. We have some time. I know. But we never have a song day on the Friday because we normally have quizzes. We don't have a quiz, but we are going to have a little bit of a lesson today just to round out the week since it's been such a crazy one. And that'll make it a little bit easier next week when we do have our quiz because Wednesday you have a early dismissal. We do. Yeah, there's a whole bunch at the beginning of the year. And that's just how it be. So what we're going to do is we're going to take a look at this homework that you totally did. And because you had plenty of time to do it, including class time yesterday. So you have no excuse at all, Coda. So basic proofs, worksheet number 1, they give us this. 2x plus 5 equals 17. We're trying to prove that x equals 6. Remember, when we're doing this, okay, we're practicing for when it's not algebra. So we're not just going to plug in 6 and be like, yep, checks out, right? What we're going to do is we're going to make this thing, the thing we're given, look exactly like that. And if we make it look exactly like that by following our rules, and our rules are not PEMDAS, our rules are the properties of equality, right? You can do it in any order you want. As long as you're following the rules for the properties of equality, you're not breaking anything. And so if we can make that look like that, then we win, right? We do our swag box and we call it a day. So first things first, as I write what I'm given, which seems silly, but it's important. So I write this, and I write why I'm able to write it, because it's given, right? So I do that. Then I'm going to do either subtraction property of equality or division property, whatever you want to do. I'm going to do subtraction first because, again, like Kanye, we want the prenup. When we do division, right, we have to divide everything, and so I'm going to have to divide this, which is no big deal, right? 2x divided by 2 is x. That's good. But then I have 5 divided by 2, which is a fraction, and I'd rather not have to subtract that later. It'll be no big deal because this will be 17 over 2. So imagine, if you will, I have 17 halves over here, and I have 5 halves over here. I'm going to subtract it. So 17 halves minus 5 halves would be how many halves? 12 halves, right? No big deal. 12 halves is just 6. So you could do division first. I'm just not going to. I'm going to do addition first. So I'm going to do 2x plus 5 over here equals 17. And then to show my work, I'll do it in red. I'm going to subtract 5 from both sides as my first step. Again, if you did division, knock yourself out. This is division property of equality, right? And then that gets us here. So therefore symbol. Now we're here. And then after that, we do what property?
What happens if we didn't put the therefore?
No big deal. I just like doing that. Whenever I don't have a reason, I like to put therefore. Honestly, you could put therefore before any of this stuff, and it would make sense. X equals 6, and that is by the division property. Oh, whoops, sorry. That is not the division property. That's subtraction property. Why did no one correct me? Division property of equality. I'm 2 steps ahead, 420, 69 IQ. What? Oh, we're getting to that. We need to pull out the orange. I like orange for my swag boxes. And we're done, okay? That's the deal. How'd you feel about number 1? Dece? Okay, for number 2, let's talk about what properties we should see. What properties should we see here, getting from here to here? What properties are we going to use? Could be any order. What property?
Addition and multiplication.
All right, so you should see the addition property being used, and we should end up seeing the multiplication. Not multiplication. Division. We got to get rid of that negative 3 times x, right? So we're going to divide. Division property. Okay? Those are the 2 that we need to see. Do I need to show all the work for you guys to be able to check it? I would hope not. They give you the answer. If you didn't get the answer, then you done goofed, right? These are the 2 things we need to see. Who needs a pen, by the way? Trade and grade. Ready? All right.
Call that Mr. Max. Evan did not.
I've got 5.
Alex needs one.
I already got one.
No, you good? All right, cool. Anybody else? All right, 5 pens. I need 5 pens back. All right, number 3. Let's talk number 3. Number 3 says, given x over 2 minus 3 equals negative 19, prove x is negative 32. This should look very familiar to a problem we did the other day, but no one's caught on to that yet. All right, so what we're going to do is 2 things. What 2 properties are we going to use to solve this in the most efficient way possible? Give me one of them.
Did you skip number 2?
Shh. I just did number 2. Addition property of equality, right? We did not skip number 2. I mean, I wrote down this stuff. I didn't show all the other stuff.
Okay.
You need to show all the other stuff. I'm just getting to the answer. That way you guys can grade it quickly. Addition property of equality, right? That's going to take care of that minus 3. And then what do we need to do to get rid of the division? Multiplication property, right? So those are the two properties I need to see. Each property is worth 1 point if you're following along at home. Questions on that?
Is the given count as one?
No, actually, you know what? Yeah, let's make the given count as 1. Yeah, let's do that. Let's do 3 points for each on the first page. Include that given. Suckers. All right. Flip the page. It says A, B, and C are collinear. Boys and girls, what does it mean for A, B, and C to be collinear? On the same line. Co means same line. Linear means line, right? So what I would do is I'd draw a picture so I know that A, B, and C are collinear. And then I would label that AB is x plus 7 and BC is negative 2, x minus 5. And this whole dumb thing is AC, and that's 5. We're trying to prove that BC equals 1, right? That's our goal. So we're going to try and take this and turn it into that, which is kind of weird, right? We're taking something that is not an equation and making it into an equation. So first things first, we should probably turn that into some kind of an equation, right? Well, how do we do that? What property are we going to use to set that up? It's not really a property. It's more of a postulate. Yeah. Not angle. What are we talking about here? Lines, which are also known as pieces of lines, which are called segments. Very good. So we're going to use segment addition postulate. Segments being added together, right? Segment addition postulate says that the little guy on the left, AB, plus the guy on the right, BC, should add up to the whole dumb thing, which is AC, yeah? Okay, cool. Now that we have that, we have an equation, which is great. But now we need numbers, right? So how do I switch these guys out for numbers? What property is the switching out property? Remember when I'm absent, you have this? Jess, what's the property where we switch stuff out? Substitution. Very good. So we're going to substitute for these guys. Substitute means plug in, right? Whenever we plug something in, no matter where we plug it in, no matter what we plug it in, we wrap it in parentheses, right? So we put in an x plus 7. Again, I don't always do this, but you are not as experienced as I am. So you need to wrap it every single time. Here we are. And that is by substitution. So now we're here. And now we can do a therefore symbol because now it's just math, right? This is stuff that we assume you know, and I know what assuming does to us. It makes it out of and, right? But I will assume nevertheless. X and negative 2x, well, that's a negative x. And then 7 and minus 5 are going to make positive 2. And then we get 5 over here. And now we should feel pretty comfortable. I'm not going to show the rest of the stuff on the left side. I'm just going to write the properties. What's the next thing I need to do? Give me one of the steps. Yeah, give me one of the steps. Your hand is up. Haha. Subtract the 2, so subtraction property of equality, SUBT, as opposed to SUBST, right? Subs property is substitution. Subtraction, SUBT, is subtraction. Don't confuse them. Sub will not be good enough for either of these. I don't know what you mean, okay? I'm all good with abbreviations as long as I can understand what it means. So we're going to do subtraction. It's going to subtract 2 from both sides, and then our last step is either multiplication or division, right? We can either multiply by a negative 1, that gets the job done, or we can divide by a negative 1. I'm going to use multiplication. You probably use division. And that'll get us that x equals, at the end of the day, yada, yada, yada. We subtracted 2, got 3, times by negative 1, we got negative 3. So what did I goof?
You gotta plug it back in.
What do you mean?
Plug the X in.
I thought I was done. No, oh, it doesn't want x equals whatever. It wants BC. Oh, man. Oh, man. So we got to plug it back in. So we write given, right, which is what we were given here. Given that BC is what? What is BC? Negative 2x minus 5. We do substitution property and we get what? Negative 2 times negative 3 minus 5. Smell what I'm stepping in here? What's negative 2 times negative 3? CX. Subtract 5. 1. And we're done. BC equals 1. Again, they want it to look like this. BC equals 1, so make sure you write BC equals 1. Swag box. We ain't got time for the orange. Questions on that one? Who forgot to do the last bit? Yep. All right, so let's count them. 1, 2, 3, 4, 5, 6 different things there. 6 points on number 4. Number 5, given D is in the interior of ABC. So we have an angle ABC. I'm going to draw that. Here's ABC. Boop. B has to be the vertex, right? And it says that D is in the interior. So here's D. a point in the interior. It says ABC is 165. That's this guy. It says ABD, that's this guy, is x over 3 plus 45. And then it says over here, which I'll do in blue, that this angle, CBD, is 3x plus 20. Nice.
Nice.
All right? Nice. All right, so now we're here. We want to prove that ABD, the measure of ABD is 55 degrees. Shrifty 5. So, this is given to us, so I'm going to just say given next to it. Now, we need to create some kind of equation here, right? Because we have an equation. We have angle ABD, its measure, equals 55. So right now we have all this mumbo-jumbo. How do we make that into an equation? What postulate will we use? Yes? The angle addition postulate. Very good. Which is going to allow us to say that this guy, ABD, that angle, plus, and the measure of it, of course, is going to equal the measure, plus the measure of the blue angle. Whoops, man, I'm jumping ahead here. Angle CBD will equal the measure of what angle? What angle name is that?
A, B, C.
Very good.
1, 2, 3.
That's right. So this guy right here plus this guy right here should equal the whole dumb thing. That is, in fact, the angle addition postulate. So angle add postulate, right? Allows us to set that up. Now, the angle addition postulate does not, unfortunately, allow you to write these numbers in right away. They don't. Because if we did that, we'd have to be specific. And remember, the angle addition postulate applies to any set of angles. So we have to be able to say angle 1, angle 2 adds up to angle 3, right, the big guy. So that's what we have here. And now, in order to get numbers, which is what we need to substitute, right? So now we're going to do the sub property. So we substitute, and we get, instead of this, we get whatever it is. And instead of this, we get whatever it is. And that's going to equal whatever this is. Danny,
Yes.
what is the measure of angle ABD in this diagram?
A, B, D, X over 3 plus 65.
Very good. All right. Next, Evan. What is measure of angle CBD in this diagram? 3x plus 20. And then lastly, we have measure of angle ABC, which is a nice number. What is it, Catherine? Katie? ABC. 165. All right, cool. Now we have an equation. Set it up, knock it down, right? After this, it's just math, which isn't too bad. Now, you're going to notice that 20 and 45, what is that going to make? 65. Very good. And we're here, right? But we also have these x's that we need to get together. Terrible idea in real life. Great idea in mathematics. Oh, here it is. Okay. So how do we get these guys together? Well, one guy's speaking in thirds. One guy is speaking in regular x's, right? So we need to get commie denomies, and we showed how to do that last time, but we're not really going to get into the nitty-gritty of how to do the algorithm. What we're going to do is talk about this. Think logically, right? How many thirds are in 1? Everybody, how many thirds are in the number 1? 3 thirds in the number 1, not halves, right? 3 thirds in the number 1. How many thirds are in the number 3 then?
9.
9! 9! 9 thirds. So we have 9 thirds here. And you can check that. Think about it. 9 thirds. Look up here. 9 thirds. Does that equal 3?
Yeah.
I know, right? So it's the same thing. It's just a different way of writing it. So we have 9 thirds here plus 1 third there. How many thirds do we have total then? 10 thirds. You could do 10x over 3 or 10 thirds of x. I don't care what you do. Okay? It's all good. So we have 10 thirds of x plus 65 equals 165. And we did that by therefore, because that's just how things are done, right? We just got stuff together. We did algebra last year. Now we're going to subtract 65 from both sides. That's what I would do personally. So that's subtraction property of equality, right? And that's going to get us this. Hundo, right? And then what would you do? What property would you use next? Yeah, go ahead. Multiplication property. Get rid of that divides by 3. So that's multiplication property. And that's going to get us 10x equals 300, like the movie. And then what are we going to do? Somebody other than him. Erica, I like your hair. What thing will we do next? Divide by 10. So division property of equality, right? That's going to get us x equals 30. And look, that's what they want us to prove, right? No, what do they want us to prove? ABD is 55. So we need to say, given measure of angle. Whoops, I shouldn't say measure angle. Should I? Should I? Yeah, I should. Measure of angle ABD equals. What does measure of angle ABD equal? Don't tell me 55. That's what we're trying to prove. What do they tell us it equals? ABD equals what? Yeah, go ahead. X over 3 plus 45. Then we do what property to switch this guy in? Substitution. So subs allows us to say that 30 over 3 plus 45 equals ABD, right? I'm going to write that over here just real small. All right, and then we do math. What's 30 divided by 3? 10 all day. 10 plus 45 is? Therefore, measure of angle ABD is 55. And then swag box. We're done. All right, for that one, here's the grand total. You ready for this? First of all, the given. As a diagram or whatever. I don't care how they did it. Okay? Then I need angle addition postulate. That's 2. Number 3, I need substitution. Number 4, I need subtraction. I told you SUB wasn't enough. SUBT. Then multiplication for 5, division for 6, substitution for 7. So 7 different things there. 1, 2, 3, 4, 5, 6, and 7. 7 points on that one. 7 points there. 1, 2, 3, 4, 5 up above, which means 12 total on that side. And then on the front side, we had 3 times 3, which is 9. 9 plus 12 is 21. So out of 21, that's what we're doing here. Out of 21. If you love your grade, turn it in. It is Friday. If you don't love your grade, keep it. Turn it in Monday. Fix it. Okay? That's the deal. Okay? All right, so that's that on that. Get out your proofs toolbox. We're going to talk about some stuff today.
You turn this in?
If you love your grade, turn it in. Yes. If you don't, turn it in Monday after you fix it. Or as soon as you fix it. Pens. I need 5 of them. I need 5. Daniel, nice throw. Hopefully you do better out in the field today.
I don't play.
Yeah, we don't
Yeah,
play
well,
today.
try not to pick it up from the sideline. That's 2.
We're spectators.
All right, third one. Here we go. Oh, nice. That was dope. See, this is why we need the other camera. He threw it right into my hand. I didn't even know I was going to catch it. It was a perfect throw. This guy should be quarterback.
Who threw it?
Oh, man. Zed.
Yeah.
You what?
That'd be like a slow motion, like,
Yeah, it's
hits his hand. It's like it matches
That was amazing.
it hits your hand, you're like,
I know, right? I could not catch it.
ESPN top 10 play.
That's right.
landed like in between his thumb and his finger.
How'd your motocross stuff go, man? Or your whatever it is. What did you do? BMX. It was BMX, not motocross.
Motocross 2 seconds.
2 seconds? Wow, that's a really short race. Okay, by definition, we have 2 things. I want you to look at opposite rays in linear pair. Did anybody get that? Okay, good. Wonderful. So, here's the deal. By definition, we have opposite rays in linear pair. Look at that page. We need to know these definitions because we're going to use them today. We're going to prove 2 theorems, our first 2 theorems we ever learned. One of which we didn't really, but we're going to learn today. Opposite rays. Hi, Ray. If 2 rays share an endpoint, forming a line, so like that, then the rays are said to be opposite because they're pointing in opposite directions. Isn't that peachy? So we know that yx and yz in this diagram form the line xyz. Therefore, they are opposite rays. That's just the definition, right? 2 rays pointing in opposite directions. Therefore, they form a straight line. Am I blowing anybody's mind?
Yes.
Okay, glad. Linear pair. A linear pair, we should know this by now. Linear means line, pair means 2, right? So if 2 adjacent angles whose non-shared legs are opposite rays, those 2 angles are a linear pair. So what I'm saying is that we have 2 angles here, right? Okay, and they are adjacent, meaning they're next to each other. See how they're next to each other? Okay, they're non-shared legs. So see how they share this leg here? That angle and this angle share leg YQ. That ray, they share it. So their non-shared legs form opposite rays. Do you see that? Right? So this is a linear pair. That's what that is. So these two angles are said to be a linear pair. We're going to have a linear pair theorem that tells us something about every linear pair. And that's going to be way more important than the definition. But just know that when you see something like that, that's a linear pair. Two angles sitting on a line, right? Their rays that they don't share form a line. Words are hard, math is easy. Do we see the diagram? Do we see that these two angles sit on a line together? Okay, that's what you're looking for, okay? So be on the outlook. Our theorem, speaking of linear pair, we have a linear pair theorem. So when you have a linear pair, there's something that's special about them, okay? And this is a theorem, meaning it is provable. It's not a postulate. So we can prove it, and we're going to. So linear pair theorem says, if two angles are a linear pair, okay? So they're already saying, take a linear pair, any linear pair, this will be true. Then they are supplementary. What does it mean to be supplementary? They add up to 180, right? So it says they're supplementary. It does not say they add up to 180 degrees. Why? Because sometimes we don't measure in degrees, right? Sometimes we measure in radians. But if they're supplementary, they're always going to add up to whatever the equivalent of 180 degrees is, right? So that's the idea there. So in radians, it would be they would add up to pi, actually. So we have a linear pair here, right? Do you identify this as a linear pair? You should. We have two angles sitting on a line, right? So we give you a linear pair. From that information, just this information, we know that these two angles are supplementary. They add up to 180, right? Because they're a linear pair, by definition, they are supplementary, right? So here we are. Now we're going to prove this thing, okay, a little bit more than this. This is a little shorthand. Let's do that now. So check it out. Proving linear pair theorem. Let these two angles be a linear pair. Now, when we prove something, oftentimes we're not given something, right? We just have to give ourselves something. We're going to say, starting from here, we're going to work our way down. Again, we're starting from the if part. If two angles form a linear pair, right? You don't have this. I have this, okay? You have this. You don't have that. Let them be a linear pair, okay? That's us saying let them be, right? If this is true, then that should be true. So let this be true, and we should be able to prove the rest, okay? So let this be true. That's our given. We gave it to ourselves. Now we're going to prove that these two angles that I just said were a linear pair are supplementary, right? That's the theorem. If they're a linear pair, then they're supplementary. So I start here, okay? Here's my diagram, so you know what I'm talking about. These two angles, linear pair, yeah? Right? Okay. By definition, they are. They have opposite rays. Then we're going to prove that they're supplementary. It's all information we need. We don't need this. That's not information. We just need to know these are a linear pair. We'll be able to prove that this is supplementary. So how do we do it? Here we go. So check it out. I know from the diagram that these two guys are opposite rays. How do I know that? Because they fit the definition, right? Right? By definition, they are. They're going in opposite direction, they're rays. Duh. So when you have a real big duh moment, almost always the reasoning behind that is because it just fits the definition, right? That's what we said it was. Why is my name Derek? Well, because by definition, that's my name. I was defined to be that way, right? That's just how it is. We don't need an explanation. That's the explanation. Next thing. Therefore, these guys form a straight line, right? That's what the definition says. If you have two opposite rays, they form a straight line, right? So I just get a therefore. Next thing, I say that angle, KJL, is a straight angle, right? We have a straight line. It's a straight angle. How do I know that? Because that's what a straight angle definition is, you dingus, right? We've talked about that. Straight angle is a straight line, right? It's 180 degrees, by the way, which we're going to use in a second. So now, we know that this guy's 180 degrees. Smell what I'm stepping in, okay? This is important because my goal is to show that these two angles right here add up to 180. In other words, they're supplementary, right? So if I can prove the whole thing's 180, then I can prove these two are 180. What postulate am I going to use, you think? What postulate? The whole thing's 180. I just proved that. My next step is to prove that these guys must add up to 180. Angle addition, right? If the whole thing's 180, then these two pieces must add up to 180 as well, meaning they're supplementary. That's the logic I'm going to use. So step one, part one of this proof was here. I'm setting it up. I'm saying the whole thing must be 180. I know that. Now I'm going to break it down, okay? So if I know that, pause. Now I'm going to go down here. By the angle addition postulate, I know that these two guys add up to the whole thing, right? That's angle addition postulate. You smell what I'm stepping in? I know this to be true by angle addition postulate. Therefore, by substitution, I don't have stuff to substitute here and here, right? They didn't tell us what these measures are, right? Maybe it's like 110, 70, I don't know, right? Could be anything. That's the beauty of this. It's any linear pair. But I do know, because I just said that this whole thing down here adds up to 180, right? So I'm going to substitute what I had here and put it there. Do Do you see I said KJL is 180, so wherever I see KJL, I can put in 180? Are you seeing it? I can't tell if you're bored or confused. Please, advise.
I don't know where these notes are at.
You don't have these notes. Check it out. We know that this is 180, right? So with this, I get that that and that adds up to KJL. KJL is 180, right?
Yeah.
So I can substitute 180 for KJL. That's all I did. So now I know these two guys add up to 180, which is almost what I wanted to prove, right? I want to show that these two guys add up to 180 because I want to show they're supplementary. Now, remember, to prove something, we have to make it look exactly like that. So if I write these two add up to 180, does that look exactly like that? No. This doesn't have any plus sign, doesn't have any 180. It says they are supplementary. So I'm not done. I'm close though, right? Because by definition, they're supplementary, right? If they add up to 180, they must be supplementary. Now I'm done. I'm going to break that down in slow-mo again, okay? And I need a response after this of bored or lost. Here we go. First off, here's my diagram. I'm given that. From the diagram, I can conclude that JK and JL are opposite rays. See how they're going in opposite directions? How do I know that? It's by definition, right? Therefore, they're a straight line. Again, part of the definition. Therefore, this angle right here is 180 degrees. Because it's a straight angle, right? Straight line, straight angle. Definition, straight angle. It's our definition. Next thing. Therefore, this thing must be 180. Smell what I'm stepping in? All right. How do we feel about part one? Easy. Easy. Wonderful. Writing it is different, right? Coming up with it yourself and doing it, it's going to be new.
Words are hard, math is
But do you see it? This is true. Words are hard, math is easy, right? That's what we're going to learn a lot this year, okay? But we're going to get better at the words. Next part, okay? So ignore all this crap. I'm going to take this right here by the angle addition postulate. I know that these two angles here add up to the big angle. That's all I'm writing. That's angle addition postulate, right? All day, baby. Then we got this, substitution. Where did I substitute? Well, check it out. I've got this guy right here that are all the same, right? KJL is 180, so whenever I see KJL, I can switch it out for 180, right? So that means these guys must equal 180, logically. Last thing. Well, that fits our definition of supplementary, right? If they add up to 180, they have to be. So that fits the def, and we're done. Do you feel better that time? Did I got you about 50, 75? All right, cool. I'll take that. Not bad for your first go. So that's proving the linear pair theorem. Let's prove vertical angles theorem. What's vertical angles theorem, you ask? Well, wonderful, great. Check in your packet. It's right underneath linear pair. Vertical angles theorem, it says if two angles are vertical, then they are congruent. Well, what is a vertical angle? Well, we define that in your notes as well. Vertical angles are any angles, I have it around here somewhere. Our vertical angles are right here. Here's the definition. It's right underneath supplementary in the definition section. If angle 1 and angle 2 are formed by two intersecting segments, so we have two segments that are intersecting. They could be lines as well, right? They intersect. And that angle 1 and angle 2 are opposite angles. Now, adjacent means next to, right? So 1 and 3 are adjacent, 2 and 4 are adjacent. 1 and 4 are adjacent, 2 and 3 are adjacent. 1 and 2 are opposite. Does that make sense? They're opposite each other, not adjacent. They're not right next to each other. See how these guys form a linear pair? That's adjacent. This is opposite, okay? So 1 and 2 are not a linear pair. They're adjacent, or opposite angles, I should say. We also can call that vertical, okay? Like this. Turns out 4 and 3 are also vertical, even though they're horizontal, right? Because you can just rotate the whole diagram. It's kind of an annoying name. But anyway, 1 and 2 are vertical angles. Everybody cool with that? Okay. That's what you should be looking for. That's the thing we're looking at. So when I go here and read the vertical angles theorem, notice that 1 and 2 are vertical, 3 and 4 are vertical, right? So if they're vertical, they say they're congruent. That's kind of neat. So 1 and 2 are always the same because they're vertical. I think of this theorem as the scissor theorem, which you should too. So check it out. I've got some scissors, right? And if I open up the scissors, I've got two intersecting segments. And as I adjust the angle of which those segments are intersecting, notice the top and bottom are always the same, right? Also notice that the sides are always the same, right? When the sides are small, this is small, right? Both sides are small, and this is big, right? So there's a relationship there. Vertical angles are always congruent. Smell what I'm stepping in? Wonderful. Scissor theorem, okay? Vertical angles theorem is what it's officially called. Let's talk about it. We'll talk about the writing in a second. Vertical angles theorem says, I lost my piece of paper. Right here. That vertical angles are congruent, right? That's what we're going to prove. We're going to prove that if you get a pair of vertical angles right like this, they're always congruent. You ready to prove it? That's our goal. So first we start out. Let them be vertical angles, right? Let's talk about some vertical angles here. And I'm going to show you that if they're vertical, they have to be congruent. So I have two angles here. I've got XYZ and AYB. Now, because whenever you create these two angles, you're going to create, side angles as well. We can use that to our advantage. Here's what I'm going to do. Preview, okay? Check it out. This guy right here and this guy right here. What kind of angles are those? Yeah. Linear pair, which means they must add up to what? 180. What about this guy and this guy? What kind of angles are those? Yeah, go again. Another linear pair. So that means these two add up to 180, and this adds up to 180. We're going to use a little bit of cutting out the middleman to prove that these guys must be the same. It's not going to be transitive, but you'll see, okay? That's the trick. These are 180, and these are 180. I can cut out this middle guy, therefore they're both equal. Okay? Here's what we're going to do. You ready for this? Bum, 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 bum. All right, here we are. My handwriting is awful, but you're going to be okay. XYZ and BYZ are a linear pair. Check it out. XYZ and BYZ are a linear pair. Confirm or deny? Confirm. Okay, we know that. We know they're a linear pair by definition, right? Just fits the definition, right? They both set on a line. The line is XYB, that angle and that angle set on a line, right? So the linear pair. Linear means line. We know that XYZ and BYZ, those two angles I was talking about earlier, are supplementary. How do we know that they're supplementary? By what theorem?
They add up to 180.
They do, but boy, what theorem tells us that they're supplementary? Linear pair theorem. Right? They're a linear pair. That means I can use linear pair theorem. That's what I did. They're supplementary. Next, that means they equal 180. Right? That's what we proved last time. Linear pairs are always equal to 180. Right? They're supplementary. Everybody cool so far? You okay? All right. That was part one. Part two. Okay? I'm going to take this equation and I'm going to rearrange it. Check it out. XYZ, BYZ equals 180. I moved the BYZ over. How did I move it over? Yeah. Subtraction property of equality. Do you see it? I took this guy here and I moved him over and now he's negative. Pretend this is A plus B equals 180. I subtracted B and moved it over. Right? That's all. Just a lot of letters. Everybody cool? All right. Next thing. I did the same thing with another set of angles. So I skipped stuff by similar logic. So I skipped doing all of this again with a separate set of angles by just saying, look, by the same logic, it's going to be this. Let me walk you through it. So last time what we did is we said this and this are a linear pair. Therefore, they're supplementary. Therefore, they're 180. Therefore, I can move stuff around in this equation, right? Cool? What I did next was I said, same thing for these two guys, right? They're both a linear pair. They're sitting on this line. This angle and this angle are both a linear pair. Therefore, they must equal 180. Therefore, I can rearrange the equation. I rearranged it. These two guys, right here and here, add up to 180. I just moved them over by subtraction. Is that cool? So I know that AYB equals all this junk, and XYZ equals all this junk. Now check it out. This junk is the exact same as that junk, isn't it? So if I equal that, and you equal that, then we must equal each other. What property is that? Cutting out the middleman. I'm touching the floor. The floor is touching Danny. Yeah, that's right. By the transitive property. That's you're touching me.
No, I'm not anymore.
Your chair. Okay. So, you smell what I'm stepping in?
You gotta pick your feet up the entire class.
That's right. I should teach like this, right? Hey, everybody. Welcome to Mr. Max Math Show. Woo! All right. So, now we're here, and we're done. Okay? These are measures. They wanted regular angle, and we know that if the measure of two angles are congruent, or equal, I should say, then that this whole thing is congruent, right? That's just the final step. Swag box, we're done. Okay, so the big thing here is this. And then we've got a little bit here with some algebra. And then we're good with transitive, right? So again, let me walk you through it. Pay attention if you haven't up to this point. These two guys are a linear pair. Agree or disagree? Okay, therefore they add up to 180. Right? Therefore 180 minus this guy gets me this guy, right? Same thing down here. These guys are a linear pair, agree? Therefore they add up to 180. Therefore if I subtract this guy from 180, I get what's left over, this guy. Okay? That's what these equations represent. 180 minus that guy gets me the guy I wanted. 180 minus the same guy gets me the guy I wanted. If that equals that, and that equals that, then they must equal each other. Transitive property. Last step, that's measure. I want regular angles, so I just say, boom, we're done. It's a little pedantic. If you forget that last step, I won't be very mad. I'll probably take off a half, right? But they want it to look just like that. That's what they asked us to prove, right? No measures, just angles. How you feel? Dece? Okay, this is not easy. It's different. It's weird. And it's like, how would I come up with that on my own? With practice. And practice means homework. So I've got some homework for you. We're going to take a look at it, okay? I know, but I also said quizzes every Friday, and you didn't object to that. So apparently it doesn't matter.
It does matter.
All right, here we go. Conjecture.
Conjecture.
What's your conjecture?
All men are superior, so that means Mr. Mac is superior.
That is not true, and I can prove it false because you are a man and you are not superior. Therefore,
Exactly. It's not. That's not. I know. I didn't say I'm superior. I said Mr. Mac is superior.
but all men aren't, and your logic is flawed because you are a man and you are not superior.
I'm not a man though.
Which means
I'm 15.
that counterexample proves everything wrong and everything that it was supporting.
He's a little boy, he's not a man.
Yeah, but sexism ain't cool, man. Not only is it not cool, but it's not cool, but it's completely false. All right, so what you are about to see are some things that we've never proven before. It's going to take some thought. So, let's take a look at these. We're not going to write anything down. We're just going to talk about it. Talk about it, okay? So, number one, it says, given that PQ equals RS. So first thing I'm going to do is I'm going to mark my diagram. PQ and RS are congruent, right? They're the same measure. Prove that PR, that's this bit, equals QS. That's this bit. All right. Okay. So let's talk about it. We've got some segments, right? We need to get to PR equals QS. Now, PR is made up of two segments. What two segments? Give me one of them. PQ and what? What's the other one? QR. So let's write that down. We know by segment addition postulate. I'll try to do this in color coding. Oh man, I chose a really bad color. This one's green. PQ plus QR equals PR, right? How do I know that? What postulate allows me to know that? We only have two of them. Yeah. Segment addition postulate, SAP. Right? Is that cool?
Of course.
Now, we also know, what about QS? What could we write about QS?
QR plus RS equals QS.
So RS plus QR equals the whole dumb thing, right? QS. Now, remember last time we used the transitive property? Right? It'd be really nice if we could say that junk equals that junk equals that, therefore they equal each other. But are they the same thing? No, they're not. They're close, right? They have QR the same, but they have PQ and RS here. So if we could make them look the same, then that means these two must be equal, right? How can we make those two look the same? Think about it. How can we make PQ and RS look the same? They're equal. They're given to us as equal, right? So by substitution, right? PQ is RS. So which one do you want to switch out? Do you want to switch out PQ for RS or RS for PQ?
RS for PQ.
All right, so I'm going to rewrite this guy as PQ plus QR equals QS. Sorry. Yep, that's fine. Yep, that's fine. And how did I do that? By substitution. SUBS.
T.
Yep, T if you want. Does that make sense? I took this guy and switched him out for that guy because we know they're the same thing. It's given to us. Right? If I told you PQ equaled 5, couldn't you substitute? Let's do it the other way. If I told you RS equals 5, couldn't you take RS and plug in 5? Well, I'm telling you RS is PQ, right? So switch them out. And now look what we have. Here and here are the exact same thing. Right? PQ plus QR. PQ plus QR. Well, if that equals PR and that same thing equals QS, then by what property does PR equal QS? Starts with a T. By what property? I cut out the middleman here. Transitive property, right? I took this and this because they're the same thing. Therefore, these must be the same thing. Transitive property. You could also use substitution. And I'll show you why that is. Okay, transitive property. You could also use substitution. See how PR equals that junk? Right? PR equals this junk. So when I see that junk down here, can I switch it out? Yeah, I can, right? Transitive property, substitution property, same thing. Same thing. You guys seem to like the transitive property. Does it make sense?
Sort of.
Okay, sort of is good. This is new. Okay? The goal, again, is to see it. And seeing it is hard. Because you've never seen it before, right? And each one of these is going to be something you've never seen before, but we're going to get used to the idea, right? Be able to see when we can get stuff to look the same, that's good. That's good. We have segments, segment addition postulate, probably going to be used, right? Down here, we have angles, right? Or at least we look like we have an angle, but really it's segments, right? They don't give us any information about the angles. They're talking about the segments. So first, mark your diagram for number 2. It tells us JK and KL are the same. JK and KL are the same. Oh, interesting. What does that tell us about point K then? What is point K? If JK and KL are the same, it's what? It's in the middle. What do we call those points? Midpoints. Very good. So K is a midpoint. That's interesting. They also tell us HJ and GH are the same. So HJ and GH are the same. And I'm using a different color. You can use double tick marks, right? And then on top of that, it says KL, that's this bit right here, equals HJ. Oh, so these two are the same. Oh, so they're all going to be the same, aren't they? Now, how do we prove that? That's what they're asking. How do we know that H or GH and JK are the same? Right? JK. So, let's write what we're given first. So we have JK equaling KL. So I'm going to write this down. JK is congruent to KL. We know that HJ is congruent to GH. And we know KL is congruent to HJ. And we want to prove over here that GH is congruent to JK. I bet we're going to use transitive property here, right? We're going to switch stuff out. We've got all this. We've got a JK here, right here, right? Here's JK, and GH is here. How do we get those to be in the same equation? That's your goal, transitive property, okay? I want you to give this a shot. It's not easy. Give it a shot. We'll talk about it on Monday, okay? You can turn the last, yeah, you can turn your warm-ups in, yeah. Again, the goal, how do we get those two in the same equation?
Did we do one Wednesday?
I don't remember.
So you can't got me points if it's not there.
No, because I'll see everybody else has one. Give it your best shot. On Monday, we'll go over this, okay?
Wasn't this part of
And then on Tuesday, we'll practice writing it in words, huh?
this part of the warm-up?
No.
This might be